All right, welcome everyone. This is the second webinar of the day. This will be on the similarities of setting oil condition alarm limit levels and how those are very similar to COVID-19. This will be predominantly presented by Michael Holloway from Fifth Order Industry. I will be available, Matt Spurlock with Delta P Reliability Services. I will be answering any questions that you put in your comment box over to the left, and I will also be available for questions after the presentation itself. Without further ado, I would like to welcome Michael Holloway.
Great. Thank you very much, Matt. Appreciate it. Joining us for our lubrication reliability in the time of COVID-19. Today we're going to talk about the similarities of setting oil condition alarm limits and the COVID-19 pandemic. This is going to be sponsored by Fifth Order Industry, Amory Reliability Centered Lubrication Services, Delta P Reliability Services, and MRG Laboratories. My name is Michael Holloway. I'm going to be joined by Matt Spurlock on the end of this webinar. A little bit about me. I'm 56 years old. I'm a proud father of a son, Max, and a daughter, Emma. I'm a subordinate of my chocolate lab, Indy. I certainly do have a healthy respect for the sea. Love sailing, but I also am terrified of the water. Go figure, right? Have a very unhealthy addiction to projects, stemming from beat-up old cars to ridiculous ideas that never seem to get off the workbench. But I do have a passion for learning. Today, we're going to talk about the similarities of setting oil condition alarm limits and COVID-19. It's based on in-service lubricant alarm limits, and they exist to provide a possible prediction of the future of failure. The development of wear as well as oil degradation, it could be linear, maybe even exponential, even logarithmic, depending upon various factors. And the spread of the COVID-19 has a similar regression. Now, this seminar ambitiously looks to cover how to go about setting alarms, exploring the similarities between failure predictions in a lubricated system and the overall spread of the pandemic of COVID-19. The topics we're going to look at today, try to do it in under 59 minutes, the regression and prediction models. How to go about setting alarms for oil analysis, and then what does COVID-19 have to do with all this? The regression analysis, it's a predictive modeling relationship tool. It's a technique which investigates the relationship between dependent variables or targets and independent variables, also known as predictors. Now, this technique is used for forecasting, time series modeling, and even finding a causal relationship between these variables. Some of the benefits include the fact that it can indicate a significant relationship between these dependent variables and independent variable. It also indicates a strength of impact of these multiple independent variables on the dependent variable. Now, the different types of techniques, mostly driven by three types of metrics, or the number of dependent variables, the type of dependent variables, and the shape of a regression line. The different types of regression analysis we're going to explore today: linear, logarithmic, polynomial, and exponential. There's a few others we won't go into. That gets into machine learning, a little bit more complicated. But for our purposes, we're just going to keep it with these four. With linear regression, it establishes a relationship between a dependent variable y and one or more independent variables x, using a best fit straight line, also known as a regression line. It's represented by an equation where y, the dependent variable, is equal to population intercept plus a population slope coefficient and an independent variable, and maybe even a random error term. Here we're looking at the difference between simple linear regressions, but there's also multiple linear regressions. And a multiple linear regression has an independent variable greater than 1, whereas a simple linear regression has only one independent variable. I want to share with you this example, simple example of a linear regression. Here we just plotted some simple data, some hours versus, say, parts per million iron. Now, what's really kind of easy to do with Excel spreadsheets is you can actually just throw this down on the spreadsheet and hit plot. What I do is just start out with a scatter graph and then hit a trend line and then ask for the equation. And then sure enough, what pops out is that your equation plus the r squared. In this case, r squared equals 1. That means we're in full agreement. It makes perfect sense. Rarely, if ever, you're going to see an r squared equal 1. Now, typically, r squared, that's an indication just how tight your model is. It goes from 0 to 1, obviously. It doesn't go beyond that. But in this case, we can actually see the direct relationship. You'll probably never, ever see this kind of direct relationship in real life, but I just want to use this as a quick example to show you what a linear regression example would look like in terms of oil analysis. With logarithmic regression, it's typically used to find the probability of something. In this case, we can use it to find the probability of failure. The dependent variable, y, is binary by nature, 0 or 1, true or false, yes or no. With logarithmic regression, there is no r squared. When we cover polynomial regression, it does have an r squared, and obviously r squared, the closer it gets to 1, the more probable and more precise the data and equation would be. We don't have that with logarithmic regressions. This is an example of polynomial regression, where y is a dependent variable and b is the coefficient for the different nth degree powers of the independent variable x. And that's starting from 0 to n. Now in this regression, the relationship between the dependent and the independent variable is modeled such that the dependent variable y is an nth degree function of the independent variable y. The polynomial regression fits into a nonlinear relationship between the value of x and the value of y. Well, there might be a temptation to fit a higher degree polynomial to get the lower error. This can result in some overfitting. Always plot the relationships to see the fit and focus on making sure the curve fits the nature of the problem. Here's an example. Especially look out for the curve towards the ends and see whether those shapes and trends make sense. Higher polynomials can end up producing strange results on the extrapolation. This is pretty straightforward to use, and it's actually rather easy to do as well with an Excel spreadsheet. If you put in your data and then hit a scatter graph, hit plot, and then trend that line, it'll provide you the opportunity to take a look at different types of equation sets. This is one way to establish that regression. You can do it by hand, or you can do it like that. If we were to compare exponential versus linear regressions, well, the primary difference is a simple one. It relates to the derivative of the function, the slope, in other words, or the growth rate. You know, for a linear function, it is constant, regardless of its value. But for an exponential function, it's proportional to the value of the function itself at any given point. And you know, as we commonly describe it, the bigger it gets, the faster it keeps growing. The spread of the COVID-19 virus, as more people get it, the faster it spreads because there are more people available to pass it on to others nearby. This is a classic example of exponential growth. Let's think about that in terms of failure opportunities within a lubricated system. Perhaps abrasive wear, oxidation, and acid buildup. These things, whether you consider this linear or exponential, the data will tell you. One procedure we can actually use to help us out in our quest to establish our alarm limits is the ASTM 7720.11. This procedure outlines two techniques to statistically evaluate the alarm limits applied to data from in-service lubricant analysis. They take a look at two different approaches, an SPC, a statistical process control, as well as the cumulative distribution curves. Now, both of these techniques, they depend on statistical information from multiple data sets, where each data set corresponds to something to be measured. And the combination of these multiple data sets covers all the alarm limits based on these measurements and sets. Now, how to create that measured or the measuring set of equipment for population? Well, first, you have to choose a test method. Here's a few examples. Particle count, ferrous density, water concentration, maybe lubricant chemistry, elemental analysis for wear, contamination, lubricant viscosity, and even wear debris analysis. With SPC, it's used to evaluate alarm limits for the measured data set and population that's fit statistically over a normal distribution. Here they're going to calculate the standard deviation for the data population and graphically represent in a parametric or normal distribution line. A lot of times we see SPCs used in manufacturing. It's quite valuable. It gives you an idea if you're in control or not. Now, it's often being said that there's certain types of tests and parameters that we look at with oil analysis where we're not talking about control. But really, we don't want to go far away from the overall spirit of an SPC. The idea is to be able to take a look at a data set and make some determination on your upper and lower control limits. Now, this graph example is taken from the 7720.11 from the ASTM protocol. It's an example of SPC where they actually establish several different limits, determine white, green, or red alarm limits. The first of which is a 1 sigma limit. 68.2% of the data sets, they fall within 1 standard deviation of the mean. That sample data, well, that's less than 1 or equal to 1 standard deviation from the center line. They're going to term that a white alarm limit. Now you have 2 sigma. This is going to be determined to be the warning limit. Now 94.45% of samples may fall within the 2 standard deviations of the population mean. And here the sample data greater than 1 standard deviation away from the center line, but less than or equal to maybe 2 standard deviations away. And that's going to be termed a green alarm limit. And then we have 3 sigma limits. These are considered the control limits. 99.73% of these samples fall within the 3 standard deviations of the population mean. And abnormal to failure conditions are suggested by this particular data greater than the 2nd and less than or equal to the 3rd standard deviation away from that center line. We're going to give that one the red alarm limit. And then there's this 4th sigma, the variance. The 99.99% of those samples fall within that 4 standard deviation population mean. That's assigned, or that's a special case variance. It's often suggested that that data exceeds the 3 standard deviations from the population mean. Now, using the average and standard deviation for each of these data sets, I'm going to go about calculating the series of tentative alarms based on that test data. For a large number of assets, or fleets, you want to select data from at least 10 different consecutive samples for each machine in that equipment population. The more consecutive samples would be expected to improve the initial quality of the alarm limits being set. And a higher number should be considered when the alarm limits are applied to, say, critical equipment rather than non-critical equipment. You don't want to selectively pick through the data or randomly pick samples from the data for this data set. Selectively picked sample data, all those values can introduce some bias for sure. Randomly picked data from a measuring data set for a large fleet, that doesn't always reflect the failure modes either. Some tentative alarm limits can be set, though, with the data population, as small as maybe, say, 7 to 10. In these cases, where all the identified failure modes and causes are not necessarily represented, lower quality alarm limits will still result. Now, these alarm limits can manually be adjusted upward through experience, according to similar machinery that you have. In cases where failure modes and causes are overrepresented, some higher alarm limits will result, and that's alarming. These alarm limits can be manually adjusted downward through experience with similar machinery, and in all cases, make sure that the alarm limits should be continually reviewed and updated either through statistics or experiences, accessing your CMMA programs, maintenance logbooks, interviews, great opportunity for failure mode effect analysis interviews. The more sample data, the more failure modes and causes are encountered, the better the data is going to be. Now here's an example of the cumulative distribution technique. An example here is a data set having some normal frequency distribution with a bell shape, a curve, and 2 tails and so forth. Now viscosity measurements often fit this form. The shearing of viscosity and viscosity improvers, typically that's what happens when you shear down the viscosity, is the viscosity improvers are actually shearing down. Those polymers, typically polymethylmethacrylate polymers, they shear down, thins out the oil. You can also get it from fuel dilution, contamination, that can occur as well with engine oils. That causes viscosity to decrease. We can also go oxidation and soot accumulation can increase viscosity. Now here's a useful way to actually establish a remaining performance value using some of this data here. We're looking to establish a tolerance alarm limit, in this case for viscosity. Now, The remaining performance value can be calculated according to the in-service values, the reference values, and the tolerance alarm limit that we've established earlier on. But keep in mind, in our equation here, our reference value has to be an absolute value. Now here's an example of initial measured value are often low, often zero, and then increases as the condition progresses. This particular scenario, well, we see this with acid number, oxidation, and even relative permittivity for examples of dielectric constant and so forth. In the equipment applications where data follows what's considered a sawtooth trend, sharply dropping to a near zero after each oil change and then increasing over time. Now in this case, we can take the data and establish a remaining performance value where the tolerance alarm limit increases from the measured. This is done for particle count, oxidation, soot development, nitration, even fuel dilution. Qualifiers may exist. We've got to apply if and then statements to 0% if it's greater than the tolerance alarm limit, and 100% if it's less than the tolerance alarm limit. Here's an example of a cumulative distribution curve for data having high reference skewed continuous frequency over a period of time. A great example of this is understanding base number, alkalinity reserve. These values start high and decrease over time, typically due to oxidation or the acid uptake. Or we're actually measuring the depletion of the functionality of the sulfonates and the phenates. Determining when to change oil is well suited for this particular type of curve. Data is progressively changing, in this case decreasing, from oil change or even top-offs. So the data values do not consistently hover about a statistical mean value. Here we can take this data and establish a remaining performance value for something that decreases over time, much like we said, the base number. Here we're looking at the remaining performance value, and that's calculated from the in-service values, the reference values, and the tolerance alarm limit. Here's an example of a generic used oil warning limit table. This is just giving you an idea what something like this would go about looking like. And quite frankly, this is really generic. You should really establish your own warning limit tables according to your asset and your environment, your application. In this case, we look at various types of things like gears, hydraulics, all the way through to EHCs. The various tests of viscosity. Now, typical warning limits for viscosity would be a plus or minus % off a new oil. That's a good place to start. For acid numbers, well, gear oil, if you have an increase of your acid number, 0.5 or up, that's alarming. Hydraulics, turbines and compressors, EHCs, a lot more sensitive. As far as water is concerned, well, different assets can take on different kind of water. Gear oil, greater than maybe 1%, whereas hydraulics, less than 0.5%. Diesel engines, 0.2. Turbines and compressors are really sensitive to water. So you want to tighten up those alarms. And there's a whole host of other things we can take a look at as well. RPVOT all the way down to insolubles. These kind of tests, typically they're relegated for turbines, maybe compressors, but quite frankly, they can be very useful for other things. Using the RPVOT for hydraulic can be very useful. And some people actually do use it for gear and diesel as well. Density is actually a really good test to run. Typically, people never consider running density-specific gravity on used oil, but it actually does indicate contamination. Flashpoint, very effective, as well as insolubles. Here's another example of a used oil warning alarm table. Taking a look at other test parameters as well. Rust, air release and foam sequence, base number, even chlorine and glycol concentrations. Setting up alarm limits accordingly. Here's another example. This is fuel dilution. You won't run fuel dilution on gear or hydraulic, but you would run it on diesel. If you see an increase greater than 1 to 5%, it becomes alarming for sure. The SAE says you can have up to 7% fuel dilution in your engine oil. I tend to think it's got to be a lot less than that, but particle counts, hydraulic systems, very susceptible. Compressors as well. Gear oil, gearboxes, it can be a lot more robust. Wear metals and additive metals, obviously, 2 standard deviations away from the center line. In case of additives, well, regardless, those metals are always going to be in there. Really what we're trying to look at is functionality, but if we actually do see an increase or decrease according to some new oils or things that are added, often we can tell if it's been contaminated with a bad add. We're going to make our determination using data, but there is trouble with data. It's not always good. It can be corrupted. We can be talking about non-robust test protocols, test methodology that hasn't been shaken out according to maybe a gauge R&R. We're going to have unforeseen influences on our data, things that we may have considered but not necessarily took into serious consideration, or something that we didn't consider at all. Sometimes our data is going to provide us information and it's going to actually have judgment and bias, unfortunately, according to our interpretation of it. And we can have confounding variables as well. And the other thing is bad math. You know, we talked about regression, and sometimes we're going to try to fit a plot. We might not be using necessarily the right regression models. Now, in terms of data integrity, we have to consider how things influence our data. Now, typically, it's not always just one scenario or event plus another will result in a third. Well, that's considered additive principle, or 1 + 1 = 2, for those of you who are inclined to understand the world in terms of equations. Well, sometimes it can be considered synergistic, where 1 + 1 doesn't equal 2, it actually equals something greater than 2, where 2 or more events or scenarios or influences combined have a greater or significantly different effect on the sum or the effects of these things applied separately. Think of the example of teamwork can produce an overall better result than if one person worked on the same goal individually and then added up. It's kind of like fifth order industry, Amory, Delta P, and MRG. Independently, we do great. Together, unstoppable. You also have potentialistic, where 0 + 1 doesn't necessarily equal 1, it's actually greater than 1, where an event becomes greater than itself without an additive or synergistic event occurring. The event becomes a catalyst for a larger scenario to evolve. And then you have antagonistic. Well, that's where 1 + 1 doesn't equal 2. It equals something less than 2, unfortunately, where 2 or more events have an overall effect which is less than the sum of the individual effects. Now consider how different scenarios play out in a lubricated asset. It's synergistic, additive, potentialistic, or antagonistic. And you'll understand why some things are not linear. Understanding how these scenarios evolve is really valuable, and understanding why is priceless. If you can determine why something went wrong, why it failed, and figure out what is required so that the next thing that happens doesn't happen the same way, you just might actually save yourself and your company a lot of money. Now, in terms of data, we can take a look at all the vast amounts of numbers and so forth associated with the in-service oil condition monitoring information that we get, even online and inline oil analysis information and what have you. Well, let's try to pull this into the whole COVID-19 thing. Why? Because, well, that's what this little webinar is all about. And given the amount of volume of research and data being collected about this novel coronavirus, it would seem like the answers ought to exist. The numbers certainly out there. The trouble is, they're all over the place. Now, the Centers for Disease Control, they forecasted about 200,000 Americans dying of this thing. And that was reported in the New York Times. Meanwhile, the Imperial College of London, well, they said that there'd be 2.2 million deaths in the United States due to this. Nobody changes their behavior. Predicting that future based on mathematical models is valuable for sure. Just like it is when we actually try to understand alarm limits and forecasting failure potential for our assets. But it's not always easy for the public or even ourselves to make sense of these results. And they can change over time, and that can be certainly confusing. That's why we want to go about understanding these models and hopefully understand this uncertainty. Understanding can help with our uncertainty, help us get us through this, help us with our asset reliability profiles and entitlements, but also try to understand what's going on with this particular scenario right now with the COVID-19. Now, let's say we try to correlate this to asset condition monitoring and this COVID-19. The number of people who actually die as a function is how many people there are, and how the virus spreads, and how many people the virus is actually capable of killing. Now, that'd be somewhat easy, right? But actually, when you start trying to fill in the blanks of that equation, things get kind of dicey. That's when you discover that there's not necessarily a single number to plug into anything in particular, and every variable is dependent on another number variable with all kinds of different possible choices and gaps in our knowledge. Now, even if an individual piece of information is somewhat sketchy, well, the problem is that whole model becomes sketchy, and that data set becomes suspect. Now, we got to consider something as basic as data entry. Different countries, different regions collect data differently, unfortunately. There's no single spreadsheet that everyone's filling in. Boy, does that sound reminiscent of a lot of oil analysis scenarios, doesn't it? You might actually have something going over to one lab in particular, and they run their protocols according to some modified ASTM test procedures, and that's all well and good. They've shaken it all out. But then you go and take that data and try to correlate it next year when you decide to use a different laboratory using different protocols. Well, they're speaking different language, unfortunately. Now, in terms of data integrity, well, quite frankly, that affects how much we can know about how many people have actually contracted the COVID-19 versus how many people have been tested positive for it. It's kind of like an asset being introduced to a contaminant, and how many of those assets will fall victim to that particular contaminant, and failure can ensue. Now, in this case, the virus itself is an unpredictable contagion, hurting some groups more than others, meaning that local demographics and even local healthcare assesses are going to be big determinants in the impact of this virus on each community. And we could say the same thing for contamination and overall application in our assets. You know, as a public health people, they're out there often working in a little bit of a dark room, trying to make sense of this all, making some best estimates with really uncertain, if not poor information. Now, some people are obviously going to die from this thing. That's maybe the last absolute thing we can obviously say. We could actually say that about assets as well. If a high degree of water is introduced into a hydraulic system that's not designed for it, that system will definitely fail. It's just a matter of time when it will fail. It's no different here. The numbers are a good model, but they are sadly pretty fuzzy right now. The thing about this is they take the virus fatality rate. Relatively speaking, the fatality rate for the COVID-19 varies widely from what they call one cohort to another. Age is a big factor. So is weight, diabetes, and other types of health considerations. These fatality rates for demographics make up, most of us, also the rate of the comorbidities. Comorbidities are either underlying diseases or conditions that can exacerbate the effects of this COVID-19. And we could say the same thing about assets. If a particular asset has silver lining bearings, really sensitive in certain environments, or perhaps a gear set has copper, and we introduce a zinc diphosphate additive into it at elevated temperatures, we can bring about a problem as well. In other words, there's no one necessarily fatality rate. Or in our cases, there's not one fatality rate with our assets per se. There are many fatality rates for this COVID-19 as well as our assets. Now let me ask you this question. Does knowing the fatality rate of this thing, say in China or Italy, tell us what the fatality rate will be in the United States? Well, it certainly helps, but that just lowers the uncertainty. It doesn't necessarily make things certain. Of course, we probably don't know the actual fatality rate in any of those places anyway, now do we? For lots of different reasons. That's true for a number of reasons too, starting with the collection of basic data about this virus, all the way through to gather, data that's gathered in different ways. We could say the exact same thing about assets, couldn't we? Even from sampling to testing to data interpretation. There's some wide variations. Big problem is sampling issues. There's also another problem of whether the data was given is actually even gathered in the first place. We don't have a reliable COVID-19 fatality rate because we don't have a reliable count of how many people have had that disease. And we could actually say the same thing about our assets if we just start out. We don't know how our assets had performed under various situations if we hadn't been testing, or if the sampling was suspect. Now, in mathematical words, we take a look at this particular equation. Fatality rate equals the number of people who died from it versus the number of people who have had it. Unfortunately, we don't know the denominator. We don't know the number of people who have had this disease. It's not unlike how many of our assets have actually experienced a certain type of failure, true failure, in the past without an autopsy, if you will, without truly understanding the root cause and doing a failure of it. You know, in an ideal world, we could test literally everyone in the population for COVID-19, proper testing, and know for certain how many people have had that disease or how many people have actually died from it due to that disease. And we could do the same thing with, say, an asset. Imagine if we could take every single gearbox ever made and put it through its paces and understand what the failure opportunities were, and then really go about establishing the reliability entitlement. There are only a couple of places it's actually been able to even get close to happening, though. One thing in particular, as far as this COVID thing, was the Diamond Princess. That was that cruise ship that got quarantined after the outbreak. A contained population density for further examination. Now that becomes real interesting. Now, in our scenario with the Diamond Princess, nearly everybody on board was tested up. There was over 3,000 samples. 3,700 people were actually on board then. Now, what's interesting here is this became a living laboratory where we have a contained population where we can examine. Imagine if we could take, say, a whole bunch of bearings and put them in a scenario, try to make them fail appropriately, and then test them up, something that maybe MRG laboratories could do for us. Well, the Diamond Princess became a living laboratory with the kind of data documentation you don't normally get around the world. Researchers are able to capture not just how many people had the disease, but also how many were completely asymptomatic, and thus likely would have been missed on land anyway, because they never showed any presentation of the opportunity for failure. The results of this suggest a setup that there are a lot of people walking around with the COVID-19 who don't know it. And as a result, that lower death rates might be actually lower than the data is actually suggested for us. Now, in terms of the Diamond Princess population, fatality rate for those people with diagnosis and symptoms was about 2.5%. But the fatality rate for all the diagnosed cases, including those that would have never been noticed, was 1.2%. Now, these are averages, by the way, and yet another example of how much uncertainty can mess with the outcomes. It turns out there's an uncertainty even there. And the actual fatality rates are really ranges of possibilities. It's calculated at 0.8 to 5.3% for all the symptomatic fatality rates that were actually presented. Between 4 to 2.7% of all those infected actually had fatality rates. So once again, even in a control scenario like this, the data can be very, very complex and confusing. Not unlike what's going on with an asset. Now, the Diamond Princess data isn't perfect. Okay, it's a cruise ship. Demographics aren't representative of a broader population around the world, and some of those sick passengers, well, they still would have died anyway. It's as if someone who had an underlying heart condition or COPD or something along those lines where they could have been diagnosed to die in the next 2 weeks to 2 years anyway, well, this scenario exacerbated it. We talked about this earlier, potentionistic, synergistic, antagonistic scenarios where it's just not additive. Well, here's a scenario where if you have an underlying situation with an asset, something promotes agitation to where it exacerbates the failure mode and accelerates. You see those passengers in the population? Some of them are sick passengers anyway, but you're not going to be able to find more reliable statistics on land than what was on that particular cruise ship, unfortunately. One of the biggest pitfalls in establishing alarm limits can be assumptions. A lot of times these assumptions, well, sometimes they're accurate, Many times they're not, unfortunately. We got to back up our assumptions with empirical evidence, with data, but the data has to be accurate. It's got to mean something. Now, just because they're assumptions doesn't mean they're wrong or useless, okay? We have to start someplace. We have to consider that we're going to start out with data that may in fact be wrong, but we have to make it more right as we go along. The models, well, we're striving to make them better each time we go. And this is why it's important of regression, taking a look at the statistics, but also understanding things like the reproducibility and repeatability and accuracy of our test methods, making sure that our sampling is sound, that we're not contributing more variables that are going to skew our information, and also that we don't have a bias according to the data, and that's how it's influencing us. But really what we have to do is drag this information in, compare it to stuff that we actually see when we pull apart the equipment on the bench, and did our data speak to the failure opportunity that was approaching? Did we listen to it? We have to go back and then adjust. And this is what can happen. This is what has to happen in order to have an increased reliability profile. So eventually we do truly understand our reliability entitlement for our assets. And I know I've used this word before, reliability entitlement. This entitlement's hard for a boomer like me to use, but the idea is that everything is entitled to some level of performance by virtue of the fact that it is what it is, right? And everything has a reliability entitlement. We just have to understand what that is. Because at the end of the day, we can honestly say this: everything will fail. We just got to figure out what that rate of failure is, what influences that failure, and how to actually slow it down. We'll never end it, but we got to slow down that failure rate. It's no different from an asset. It's no different than this viral pandemic that's going on. Use data, use science. Don't go on assumptions, don't go on emotion. There's an old saying, when emotions are high, logic is low. When logic is high, emotions are low. If you're going to make a decision, often it has to be predicated around logic. The topics we set up to cover today is understanding regressions and prediction, how to go about setting alarm limits with oil analysis, and drawing a comparison and correlations and so forth on the COVID-19 and what that has to do with actually setting alarm limits and getting a better understanding of both worlds, if you will. I'm going to take some questions and answers now. I want to introduce Matt Spurlock. Thank you very much for attending our webinar. We look forward to doing this again.
Yeah. Thanks, Mike. All right, so I see one question in the comments section. It says, can you please suggest the alarm limits for iron or other ferrous content for different equipment like gearbox, hydraulics, and steam turbines? And what I would like to address here is that it's not a function of being able to say or to answer you with saying that this is the alarm limit that you should have for your gearbox, your hydraulics, or your steam turbine. It's just not the case. In fact, when we really begin looking at how we utilize those statistical alarms, we start off on a very broad basis. We can say, okay, based off of statistical analysis, the second and third standard deviations will be our caution and criticals for gearboxes in general. And then really to be relevant, we need to fine tune that. We need to know what's the make, what's the model of the gearbox, what's the sump volume. We can find that through the make and the model. And then if we want to get even more specific, we need to narrow it down to that specific piece of equipment. So it all boils down to what is normal, preferably for that piece of equipment. If we can't get enough sample points from that piece of equipment, then we look at what's normal for that particular make and model under those similar operational type conditions. So I can't in good faith sit here and say, well, your gearbox oil alarms for iron should be set at 50 ppm across the board. If you do that, you are asking for problems. Same thing with hydraulics, same thing with steam turbines. It just boils down to being able to understand how to do that statistical analysis and calculate those standard deviations. Are there any other questions that anybody has for us?
And Matt, just to pick up on where you left off until we get a couple more coming through, that's a great point. And you know, for those of you out there, if you want to crunch the data, it becomes really simple if you use Excel. Excel spreadsheets. It's ridiculously simple. You can actually, I don't know if you all, when you're in college and whatnot, had to do, or high school or junior high, whatever you're doing, algebra 2, and you're starting to understand how to do regressions by hand, pain in the neck. But I tell you what, if you actually use Excel to do that, it becomes a lot simpler. And then you can actually also develop data on standard deviations and work from that. And Excel is just so valuable and so powerful to do these things, makes things really easy. I was starting to mess with trying to develop systems to compare different types of regression models and then work off the closest R squared to 1 and then use that as a intelligent model going into it, and kind of started busting into some machine learning using those algorithms too. So, but it's all coming out of Excel. So those of you who like to play with that, it's a great program, great way to start crunching the data to make sense for you.
And also on that, if you're going to dump your data into Excel, if you have a large amount of data points that you think you're going to use for your analysis, before you even think about doing the statistical analysis piece to find out what your standard deviations are, you've got to follow a process to remove the outliers, because you're going to have some equipment or some numbers that are outliers on the high side. You're going to have some values that are outliers on the low side. You don't want those outliers giving you a false sense of security or a concern. Another question just came in. How much important is it to refer to OEM condemning and alarm limits for equipment? That is an excellent question, because you've got some manufacturers out there that will say, if your iron level reaches 150 ppm, you should change the oil. That's what you get from the OEM. And first off, changing the oil, if the properties of the lubricant are still good, changing the oil is not going to do anything to address the presence of high iron. It's just going to remove a small percentage of that iron, because you're going to have a lot of that still left over as a residual. So the OEM condemning alarm point is a starting point. So if you have a situation where you have no history, you don't know, the laboratory you're using doesn't have any history on your particular piece of equipment, your particular make and model, likely they will have something, then you can utilize that OEM condemning point. And I'm talking specifically around wear debris first. You can use that OEM for the first few samples. But obviously, the more samples we have, the more relevant your statistical analysis is going to be, and the more accurate. But we can accurately set a pretty decent trend just after your third sample. After that third sample, we can begin to understand what is normal for that unit. So it's a good starting point, but you're eventually going to want to get away from that OEM limits as far as wear debris. Now, as far as fluids, the OEM, the Exxon Mobils, the Shells, the Chevrons, the whomevers, the engineered lubricants, LEs, they should have what they consider condemning points for their fluid properties. We have a rule of thumb, plus or minus 10% for viscosity. Michael had a great table for rules of thumb for some of the other fluid properties. But really, you can work with the OEM to determine what they consider condemning for their fluids. You can also work with the laboratories, because they've got thousands, tens of thousands of samples of data for different fluid types. So they can kind of assist you with that as well. And then see, somebody else wrote, when we look for a solution using the analogy, if we look for a vaccine, designing the equipment, how many individuals need to participate in the experiment? Okay. Talking about equipment, how many pieces of equipment need to be tested in order to infer the rest will behave the same way? And what's the statistical fundamental supporting the number? Interesting question, Daniel. All right, so I'm going to take a stab at this question, and then this is actually kind of feeding into the regression and forecasting model that Holloway was talking about. So I'll take a stab at this first, and then I'll let Holloway kind of follow it up if he would like. So as far as how many pieces of equipment do we need to be tested in order to infer the rest will behave the same way? The challenge there, Daniel, is that all of the variables in order to say that everything else is going to behave the same way, then you need to have the exact same variables in order to do that. So, and even then with machines, you've heard the phrase, I've said it, and a lot of people that have taught these classes have said it, that you can have two machines, two pieces of equipment right beside each other doing the exact same job, the exact same environmental conditions, but one of them is going to wear differently than the other. Okay. Now, in reality, is it going to be a significant amount of wear? It could be, most likely not, but it certainly could be, because a lot of that depends on how long has each one been in service. What was the machining process like on the internal parts beforehand? Did one of them have a higher concentration of break and wear than the other one? So it's difficult to actually get two machines, even side by side, to where all the variables are the same. Now, we can kind of infer the way this machine is going to function moving forward, but I believe it's going to be difficult to determine how all of these machines, of these same types of machines, will react moving forward without monitoring each one. Michael, do you have any feedback you want to add on that?
It's great. It is a good question. And the thing is that, and just to come off of your bootstraps and saying, is that obviously every asset and every condition, every environment is going to be different, but statistically speaking, typically if we look at the cumulative distribution, you always want to, rule of thumb is about 30 samples or 30 data points. To make anything statistically accurate, 30 has always been the magic number. You can go down to 10 data points if you feel like you have some semblance of control, or there's not too many outliers or too many confounding or biasing opinions and to really confuse the data. So 10 data points can work if you're looking at something that's not ridiculously polynomial, that can really start, not linear either, but it's not a really second or third order polynomial type regression. So 10 sample points is good. You can actually even, in some cases, whittle it down to between 5 and 7 that I've seen. Anything less than 7 sometimes gets a little what we call dicey, because we just don't really have enough information. Now, the other thing that also comes into play too with that, when we start taking a look at the data, is the time span and the rate in between what we consider to be our initial all the way down to our failure point. And if we're running data and we're looking to where we're actually establishing a decent trending, and we're not really getting towards what we would consider our biased failure point, then things are actually going to be a lot more predictable. But when we actually run it all the way through and things fail within 5 or 7 data points miserably, we realize that we probably should, if we could get a little bit more information in between those two points, our model would be even better. So short answer is 10 samples, and in between the failure opportunities definitely puts you in a good spot. If you get up to between, more than 30, be excellent, because like we said, the more data, the better, provided you're not taking too much consideration on some of these outliers and you don't understand where the outlier data is coming from. It can create bias and confound you, and quite frankly, really send you down a rabbit hole you don't want to go into. You could overfit. If you overfit a polynomial regression, it becomes really weird. If you underfit it, it becomes almost linear, and that's not true either. I've never seen a true linear relationship in data anyway when it comes to oil analysis. It really is true, mostly polynomial. Every so often it's exponential, but it's really a polynomial function. So try to get, like I said, have at least 10 data points. Does that help out? Hey, Matt, I also got another question in here. It was on, if we were just starting out a program and have a few samples, or we have a unique type of machine, what's a strategy for setting this up with a unique type of machine or a unique application?
Yeah, I saw the same question. That's an excellent question. So when we hear the term unique machine, first off, I'm in a lot of facilities, optimizing a lot of oil analysis programs, and I hear people all the time tell me, "Well, we're different. We're different. We're different. You don't understand. We're different." There's only a very small percentage of lubricated parts that are actually unique and different. Just about everything that we have that is lubricated with oil is either a gear, a bearing, a bushing, a slideway. Okay. Even if we look at diesel engines, okay, which arguably a lot of our bigger oil labs live and breathe by diesel engine samples. A lot of the pistons moving up and down, that's just sliding. That's rings sliding on a seal of oil through a cylinder liner. So what we do is we can, at least what I do, because based off of my experience working in facilities, being out there on the front lines of maintenance and condition monitoring, honestly, a lot of what I'm going to do is going to be based off of experience. Michael Holloway might do things a little bit different. Rich Wurzbach might do things a little bit different from there. And Mike Johnson might look at it a little bit differently from there. But we're going to set the alarm based off of experience. We're going to have a conversation with you, ask you, what exactly is this equipment? What is inside? What are the lubricated parts? So that we can at least come up with some type of mathematical process of assigning that initial alarm point. Okay. Combine that with our own experience itself.
That's a great point, Matt. And I know Johnson wants to chirp in here too, because he's got a lot of experience in this world. One thing though, and I will say, going into a unique environment, and it's like anything else. Any of y'all that ever spent any time in a process plant or chemical engineers, I remember way back when I was a much younger man, in a process plant, a lot of times before we started doing a brand new reaction in one of the reactors, we'd sit down with EH&S and we'd plot out do a hazard review and figure out all the different ways in which we could blow up the place. And some of them were obviously pretty, well, we're definitely on board, and other things were outlandish. A meteorite hitting the building would be ridiculously outlandish, but we had to list down every possible opportunity for failure. Some of them were given more weighting than others, but here's where logarithmic regressions come into play too, because now we're actually trying to understand the odds of something happening, the probability of it. And doing a quick log regraph on it actually does help you with that, and it's not that difficult to do. You can really assess to say, okay, of all the ways in which my lubricated system is going to fail, to Matt's point, there's only several different scenarios in which the lubricant is actually doing the thing, okay? And there's probably only several more scenarios where we have a true failure opportunity. There may be some outliers, some rare occurrences, but if we start understanding the various failure opportunities that are presented into the system, we start seeing some very, very generalized things coming through, and that's when we can start shaking out the data. In some environments, obviously, they're going to be a lot more maybe abrasive contaminants. There's others that are going to be perhaps wetter. There's others that are going to bring about more oxidation or a viscosity break, whatever it is, though. By listing them all out and then going through the probability of these things, taking that, modeling it, and then going back after some data has been coming through to see if your model actually worked, to see if you're how far up to your R-square was. Can't do it logarithmic, but for your polynomial, then all of a sudden now you can truly predict the future. Trust me, I mean, I've done this. It's actually pretty surprising. Math doesn't.
Okay, Matt, are you still there? Well, this is Mike Johnson. Yeah, I'm going to toss in there. Both you guys hit the nail on the head, I think. When you look at a unique machine, you got to boil machine interactions down to the simplest common denominators. We either have sliding contact or rolling contact. Where we have rolling contact, we're looking at iron on iron, and we can follow statistical models that represent other iron on iron contacts. Where it's a sliding contact, we have dissimilar metals almost uniformly. We can apply whatever models we wish to use for brass against brass, bronze, Babbitt against iron. So while there are many different machine designs and there are some truly unique machines, you look inside the machine, you find rolling and sliding contact, elasto-hydrodynamic and hydrodynamic oil films, and the behaviors of the machine's parts within those operating contexts are going to look real similar to what we see with other machines. Well, that's all I got, Matt.
And then, like I said, what we're going to do is we're going to, after that third sample, be able to establish what a normal trend is, or what it appears to be, and then start doing mathematical data the more samples we get. We've got one more question that popped in. Is it good to change oil if physical chemical properties are above condemning limits, but wear debris are normal? If recommended but not changed, will it have impact on equipment? Thank you. All right, so I would love to address this. This is something near and dear to my heart. If the chemical properties of the lubricant are above the condemning limits, then you absolutely must change the oil. There's no question about it. It doesn't matter if there's wear debris present or not. And here's why. How long do you want your equipment to run with condemned oil, with unserviceable lubricant? You don't, not at all. That's why we have different levels of alarms on fluid properties. If the physical chemical properties of the fluid are in that cautionary, that initial alarm, that's when you want to schedule the oil change, because you don't want to wait until after it's condemned, because at that point, the fluid is actually going to begin doing more damage than what it is good. The same thing holds true when we look at particles and moisture. Our equipment can run without damage if you have particles and moisture, but not for very long. Our equipment can run with condemned oil, but not for very long. At some point, that condemned oil, that fluid that's got poor viscosity, it's got high oxidation, it's got a high acid number, okay? The idea is that you take a proactive approach. That's why we're monitoring the physical properties to begin with. Because remember, we have three categories in oil analysis: machine health, which is predictive, and then fluid health and contamination level. Both of those are proactive in nature. So the idea is that we're monitoring these proactive aspects of the oil. And when we identify that something is wrong, we do something about it before the machine hits point P on that P to F curve. That's where you're going to get value. So absolutely, if you're above the condemning limits on fluid properties, you absolutely must get that fluid out of there. And depending on how far above those condemning limits are, you may need to actually do a complete flush of the system. Because remember, as much as 30% of the volume of the entire system could still be left behind in the form of residual. If we take a hydraulic tank as an example, there's much more hydraulic fluid in a hydraulic system than just what we have in the tank. Okay, so I know that's a rather long answer, but yeah, if they're above the condemning limits, get it changed out, regardless of what wear debris is. All right, Mr. Holloway, you want to wrap it up? Maybe Mr. Holloway's having some audio problems. Listen, everybody, thank you very much. There's a survey to fill out when we're done, so please let me go ahead and finish up this seminar. If you have any questions, feel free to reach out to anybody on this group. Reach out to us through LinkedIn or what have you. Appreciate you all stopping in. You can email us more questions anytime you want. So I appreciate it. Be safe and take care.